Somewhere in a physics classroom, a simple equation drawn on a whiteboard quietly closes a door that science fiction has spent generations trying to pry open. The idea of moving faster than light feels, at first glance, like an engineering problem. Build a stronger engine. Find a lighter material. Push harder. But the deeper physicists looked into the nature of speed, motion, and time, the more they realized the barrier is not made of metal or fuel. It is woven into the structure of causality itself. This is not a story about impossibility for its own sake. It is a story about consequence. When Albert Einstein reshaped our understanding of space and time, he did not simply describe a speed limit. He revealed that speed, time, and order of events are all tangled together in ways that no one before him had fully grasped. Exceed that limit, even in principle, and the tangle does not just stretch, it breaks. What follows is an investigation into why faster-than-light travel is not merely difficult, but paradoxical. Why effect could come before cause, why a message could answer a question never asked, and why some of the most careful minds in physics have spent decades chasing loopholes in their own laws. Some of those loopholes are still open. Others have quietly closed under the weight of evidence. To understand why, we have to start with the constant that makes all of this possible and impossible at the same time. The speed of light is not simply the fastest thing we have ever measured. It is a boundary condition built into the geometry of the universe, and every experiment designed to test it has only reinforced how strange that boundary really is. Light does not simply happen to be fast. It occupies a unique position in physics as the speed at which cause and effect propagate, the speed at which information itself is permitted to travel, and the speed that every observer, no matter how they are moving, will measure as exactly the same. That last point is the one that unravels most people's intuition the first time they encounter it. In everyday experience, speed is relative. If a person is walking forward on a moving train and tosses a ball ahead of them, an observer standing on the platform sees the ball moving faster than someone standing still on the train would perceive it. Velocities add. This is common sense, refined over centuries of observation, and it works perfectly well for trains, cars, and thrown baseballs. But light refuses to play by that rule. No matter how fast an observer is moving toward or away from a beam of light, they will always measure it traveling at the same speed. Chase a beam of light at half its velocity, and you will not see it slow down relative to you. You will still measure it moving away at full speed, as if your own motion did not matter at all. This was the puzzle that occupied physicists near the end of the 19th century, when a series of delicate optical experiments failed to detect any variation in the speed of light due to the Earth's motion through space. The expectation had been that light should behave like sound, or water waves, or any other disturbance moving through a medium. Its measured speed should shift depending on the observer's own velocity relative to that medium. Instead, the experiments returned a result that seemed to defy logic. No matter which direction the measurement was taken, no matter the season, no matter the Earth's position in its orbit, the speed of light came back the same. The medium that scientists had assumed carried light through space, sometimes called the luminiferous ether, could not be found. It was not there to be found because it did not exist. It took a young patent examiner working in Switzerland to recognize that the problem was not with the experiments. The problem was with the assumption that space and time were fixed, universal backdrops against which motion simply happened. Einstein proposed instead that the speed of light is constant for every observer precisely because space and time themselves are not fixed. They stretch, compress, and shift depending on how an observer is moving. Time is not a single ticking clock shared by the entire universe. It is a personal measurement, unique to each observer's frame of reference, and it can run at different rates for people moving at different speeds relative to one another. This idea, formalized in 1905, became known as special relativity, and it rests on two deceptively simple postulates. The laws of physics are the same for all observers moving at constant velocity relative to one another, and the speed of light in a vacuum is the same for all such observers, regardless of the motion of the light source or the observer. From these two statements, an enormous structure of consequences unfolds, and the consequences are what make faster than light, travel more than a distant afterthought and instead a direct trigger for a chain of contradictions. To understand why, it helps to look at what happens to an object as it approaches the speed of light within this framework. As velocity increases, the energy required to accelerate that object further does not increase in a straightforward linear way. It increases according to a relationship that grows without bound as the object's speed approaches that of light. In practical terms, this means that accelerating a massive object to the speed of light would require an infinite amount of energy. Not a large amount, not an impractical amount, an infinite amount which no finite source of energy in the universe could ever supply. This alone explains why no spacecraft, no particle accelerator, no imaginable future technology built from ordinary matter could ever push an object with mass to light speed, let alone beyond it. Particle accelerators offer a working laboratory demonstration of this effect every single day. Facilities designed to accelerate protons and electrons to tremendous velocities can push these particles arbitrarily close to the speed of light, but never to it and never past it. Instead, as more energy is pumped into the particles, their velocity increases by smaller and smaller increments, while their effective mass, or more precisely their relativistic momentum, climbs steeply. The particles behave as though they are becoming more resistant to acceleration the faster they go, a phenomenon perfectly predicted by relativity and confirmed with extraordinary precision. This is not a limitation of engineering. It is a limitation woven into the relationship between energy, mass, and velocity itself. But energy requirements, as decisive as they are only the first layer of the problem. Even if some hypothetical form of matter existed that did not require infinite energy to exceed light speed, a second and far stranger consequence would emerge, one that strikes not at engineering, but at the logical structure of time itself. This is where the story shifts from why faster-than-light travel is difficult to why it may be fundamentally incompatible with a universe that behaves in an orderly, cause-and-effect manner. Consider what relativity says about time dilation. As an object's velocity increases relative to an observer, time for that object appears to run slower from the observer's perspective. This is not an illusion caused by signal delay or the time it takes light to reach an observer's eyes. It is a real physical effect, confirmed repeatedly using atomic clocks flown on aircraft, satellites in orbit, and particles moving at high speed in laboratory experiments. A clock, moving relative to an observer, genuinely ticks more slowly, and the faster the relative velocity, the more pronounced the effect becomes. As velocity approaches the speed of light, time dilation approaches a point where, from the outside observer's perspective, time for the moving object would effectively stop. This relationship suggests mathematically that if an object could somehow cross the threshold of light speed, the equations describing time dilation would demand that time for that object become imaginary in the mathematical sense, involving the square root of a negative number. Physicists do not interpret this as time literally becoming imaginary in some mystical sense. Instead, they interpret it as a signal that the equations of special relativity simply do not describe a physically sensible situation beyond that threshold. The mathematics does not gracefully extend past light speed. It breaks down entirely, refusing to offer a coherent description of what such motion would even mean. This breakdown becomes especially significant when combined with another relativistic effect, the relativity of simultaneity. Because different observers moving at different velocities experience time differently, they can also disagree about the order in which distant events occur. Two events that happen at the same moment according to one observer might happen at different moments and even in a different sequence according to another observer moving at a different velocity. Ordinarily, this does not cause any practical problems, because for events connected by signals traveling at or below the speed of light, there remains a strict, unambiguous separation between cause and effect that all observers agree upon, even if they disagree about exact timing. But faster-than-light signals shatter this agreement completely. A signal that moves faster than light can, in some valid reference frames, be observed traveling backward in time, arriving at its destination before it was ever sent. This is not a hypothetical curiosity confined to chalkboards. It follows directly and unavoidably from the mathematics of relativity once faster than light motion is permitted. And it opens the door to a class of problems that occupied physicists for decades afterward. Problems involving causality, information, and the unsettling possibility that a universe allowing faster than light travel might also be a universe that permits effects to precede their own causes. The stakes of that idea are difficult to overstate. Causality, the principle that causes precede their effects, is not simply a philosophical preference. It is one of the deepest assumptions underlying nearly all of physics, chemistry, and biology. Every equation describing how systems evolve over time assumes that the future is built from the past, not the other way around. If faster than light travel truly permits information to move backward through time under certain conditions, then it does not merely violate a speed limit, it threatens the logical scaffolding that allows science to make any predictions about the world at all. So the question becomes not simply whether faster than light travel is technologically difficult, but whether the universe's own internal logic actively forbids it, using energy requirements as a first line of defense and causality itself as the deeper, more fundamental barrier behind it. Physicists exploring this question did not stop at hypothetical spacecraft. They began asking what would happen if a particle existed that had never been slower than light to begin with, a particle born already moving faster than the cosmic limit, and whether such an object could exist within the framework of relativity without breaking it entirely. In the 1960s, a small group of physicists posed a question that seemed almost mischievous in its simplicity. Special relativity forbids any object from crossing the light speed threshold from below, because doing so would require infinite energy. But what if a particle simply never needed to cross that threshold at all? What if a particle existed that had always moved faster than light from the very moment of its creation and would always continue to do so? Such a particle would never need to accelerate through the impossible barrier because it would never have been on the slower side of it in the first place. This thought experiment gave rise to a hypothetical class of particles named tachyons, drawn from a Greek word meaning swift, and their proposed existence forced physicists to take the mathematics of faster-than-light motion seriously rather than dismissing it outright. The idea was not idle speculation invented for entertainment. It emerged from a careful examination of the equations of special relativity themselves. Those equations relate an object's energy, momentum, and mass in a precise mathematical relationship. For ordinary particles moving slower than light, this relationship behaves in a straightforward way. But physicists noticed that the equations do not technically forbid a second class of solutions, ones in which an object's mass, in a particular technical sense, becomes what is called imaginary. An imaginary mass sounds like nonsense at first hearing, but within the structure of the mathematics, it does not produce nonsensical results. Instead, it produces a particle whose calculated energy and momentum remain perfectly real numbers, provided that the particle's velocity always exceeds the speed of light. In other words, the equations seem to permit a particle that could never slow down to below light speed, in the same way ordinary matter can never speed up to reach it. This symmetry appealed to physicists on a conceptual level. If normal matter is forever trapped below the light barrier, then perhaps nature includes a mirror class of matter forever trapped above it, with the light barrier serving not as an absolute wall, but as a kind of forbidden middle ground that separates two distinct regimes of existence. Slower than light particles, referred to as tachyons or simply ordinary matter, would occupy one regime. Faster than light tachyons would occupy the other. And, crucially, according to this framework, neither type of particle would ever be required to pass through the barrier itself, since tachyons would begin their existence already on the far side of it. But elegant mathematics does not automatically translate into physical reality, and the tachyon hypothesis ran almost immediately into the same causality problems that plague faster than light travel in general. If tachyons exist and can interact with ordinary matter, sending or receiving signals, then the relativity of simultaneity comes back into play with full force. A tachyon signal sent from one location to another can, depending on the relative motion of the observers involved, be interpreted as traveling backward in time from certain reference frames. This is not a flaw in a particular version of the theory that could be patched with a small adjustment. It is a direct consequence of combining faster-than-light motion with the framework of special relativity, which treats all observers moving at constant velocity as equally valid perspectives on the same events. To make this concrete, consider two observers moving at different velocities relative to each other, each capable of detecting tachyon signals. According to one observer, a tachyon signal might be sent at a certain moment and received a short time later at a distant location, appearing to move forward through time in a perfectly ordinary way. But according to the second observer, moving at a different velocity, the same sequence of events might be interpreted differently. The reception of the signal from this second perspective could occur before its emission. The mathematics of relativity does not merely allow this reinterpretation as an approximation or a rounding error. It requires it as a rigorous consequence of how simultaneity and ordering work for anything moving faster than light. This is where the tachyon hypothesis, despite its mathematical elegance, ran into a wall that no amount of theoretical refinement could remove. If a tachyon signal can be interpreted as moving backward in time from some valid reference frame, and if tachyons can be used to transmit information, then it becomes possible, at least in principle, to construct a scenario in which information sent by one observer influences events in that observer's own past. Physicists in the field explored this exact scenario using what became known as tachyonic anti-telephones, devices that would theoretically use faster-than-light signaling to send messages that arrive before they are transmitted when observed from certain frames of reference. The implications of such a device are not simply strange, they are logically self-defeating in a very specific way. If a message can be received before it is sent, then the recipient could, in principle, use the information contained in that message to prevent the original sender from ever sending it. This is not a poetic flourish borrowed from science fiction. It emerges directly from applying the accepted mathematics of special relativity to a hypothetical faster-than-light signal, without adding any additional assumptions beyond what the theory already contains. The mere existence of a mechanism for backward causation, however exotic, threatens to unravel the entire chain of cause and effect that physics depends upon to make consistent predictions. Faced with this problem, physicists explored several possible responses, each revealing something important about how deeply causality is embedded in the structure of physical law. One response was simply to conclude that tachyons, whatever their mathematical elegance, cannot exist as physical particles capable of carrying information, precisely because their existence would violate causality in a way the universe does not seem to permit. Under this view, the equations of relativity technically allow imaginary mass solutions, but nature simply does not populate the universe with objects that satisfy them, in the same way that a mathematical equation might have solutions that do not correspond to any physically realized system. A second, more nuanced response distinguished between different types of faster-than-light phenomena. Some processes might exceed the speed of light without actually transmitting usable information, and such processes, it was argued, might be permissible without threatening causality, since causality violations specifically require the transmission of information or influence that could affect events in the past. This distinction becomes critically important later in the story, when examining phenomena such as the expansion of the universe and certain quantum effects that superficially appear to involve faster-than-light influence, but do not, upon closer analysis, allow for actual information transfer. A third response, more radical still, questioned whether the mathematics of special relativity should be trusted at all in describing hypothetical, faster-than-light regimes, given that the theory was developed and tested using observations of matter and light moving at or below the speed of light. Extrapolating the theory's equations into a domain it was never designed to describe, some physicists argued, might simply produce nonsensical results that reveal the limits of the theory's applicability rather than genuine insights into a hidden, faster-than-light universe. Despite decades of theoretical investigation, no experimental evidence has ever confirmed the existence of tachyons. Searches conducted using particle accelerators, cosmic ray observations, and specialized detector experiments designed specifically to look for particles exhibiting the signatures predicted by tachyon theory have consistently returned null results. This absence of evidence does not by itself prove that tachyons cannot exist, but it aligns with the theoretical argument that causality violation may represent an actual physical constraint on the universe, not merely a mathematical inconvenience that an undiscovered particle might someday circumvent. What makes the tachyon story so valuable to this broader investigation is not that it definitively resolved the question of faster-than-light travel. It is that it forced physicists to confront in precise mathematical terms exactly what would go wrong if faster-than-light motion were physically real. The problem was never simply that no known particle moves that fast. The problem was that the very act of moving faster than light, combined with the well-established and repeatedly verified principle that different observers can disagree about the order of distant events, produces logical structures capable of generating contradictions. A signal that can arrive before it is sent is not an inconvenient side effect to be worked around with clever engineering. It is a direct assault on the coherence of cause and effect, and it suggested to many physicists that the light-speed barrier was never really a statement about speed alone. It was a statement about the preservation of causal order throughout the entire universe. This insight sets the stage for a deeper examination of how relativity handles the relationship between distant events, an examination that requires stepping away from hypothetical particles and looking instead at the geometric structure that relativity uses to describe which events can possibly influence which other events, a structure built from something physicists call the light cone, and one that reveals with startling visual clarity exactly where the boundary between ordinary causality and paradox actually lies. Physicists needed a way to visualize causality itself, something that could show without ambiguity which events in the universe could possibly influence which other events, given that nothing can travel faster than light. The tool they developed for this purpose is called a light cone, and despite its simple geometric appearance, it may be the single most important diagram in the entire framework of relativity. Imagine a single event, a flash of light occurring at one specific point in space and one specific moment in time. As time moves forward from that instant, the light from the flash spreads outward in an expanding sphere, always moving at exactly the speed of light in every direction. If this expansion is plotted on a diagram where one axis represents time and the other axis represents space, the resulting shape is a cone, opening upward into the future. Every point along the surface of this cone represents a location that the light could reach at a given moment, and every point inside the cone represents a location the light has already passed, or a location that something moving slower than light could still reach. This is called the future light cone of the event. There is a mirror image of this structure extending backward in time as well, called the past light cone. It represents every event that could have possibly sent a signal, traveling at or below the speed of light, capable of reaching this central event. Together, the future and past light cones divide the entirety of spacetime into three distinct regions relative to any given event. There is the region that the event can potentially influence, which lies within its future light cone. There is the region that could have potentially influenced the event, lying within its past light cone. And then there is everything else, an enormous region that lies outside both cones entirely, referred to as space-like, separated from the original event. This third region is where things become genuinely strange, and where the deep connection between light cones and causality becomes clear. Events that are space-like, separated from one another, cannot influence each other in any way, according to relativity, because doing so would require a signal traveling faster than light to bridge the gap between them within the available time. Crucially, because different observers moving at different velocities disagree about simultaneity, they can also disagree about the temporal ordering of two space-like separated events. One observer might measure event 1 as happening before event 2. A second observer, moving at a different velocity, might measure event 2 as happening before event 1. Neither observer is wrong. Both measurements are equally valid within their own reference frames, because relativity does not privilege any single observer's perspective as the true objective ordering of events. This might sound like an abstract technicality, but it carries a profound implication. As long as no signal faster than light is required to connect two events, this disagreement about ordering causes no logical problems whatsoever, because neither observer's measurement implies that one event caused the other. Since the events are space-like separated, causation between them was never possible in the first place, regardless of which one appears to happen first from any given perspective. The universe tolerates this ambiguity perfectly well, because ambiguity about the order of unconnected events does not threaten cause and effect. It only threatens cause and effect for events that are supposed to be causally connected. This is precisely why faster-than-light travel poses such a severe problem. A signal or object moving faster than light does not stay confined within its light cone. It travels into the space-like separated region, connecting two events that relativity's own geometry says should have no fixed temporal order. But if such a signal actually carries a cause and effect relationship between them, some observer, moving at some particular velocity, will inevitably measure the effect as happening before the cause. This is not a distortion caused by limitations in measurement technology. It is a direct, unavoidable consequence of the geometry of space-time itself, once causal influence attempts to travel outside the light cone. Physicists sometimes describe the light cone as drawing a boundary around what is knowable and influenceable from any given point in space-time, a boundary enforced not by any physical barrier in the ordinary sense, but by the mathematical relationship between space, time, and the constant speed of light. Every particle of matter, every photon of light, every signal ever transmitted by any technology humans have built or are likely to build, remains confined within these light cones throughout its entire existence. This confinement is precisely what preserves the consistent, agreed-upon ordering of cause and effect across every observer in the universe, regardless of how fast or in what direction they happen to be moving. Understanding this geometric picture makes it possible to see exactly why the tachyonic antitelephone described earlier produces such a severe problem. A tachyon, by definition, moves faster than light, meaning it necessarily travels outside the light cone of the event that produced it. It carries information into the space-like separated region, a region where temporal ordering is not fixed, but instead depends on the observer's frame of reference. If that information is then used to transmit a reply, potentially using another faster-than-light signal traveling back through a different observer's space-like region, it becomes mathematically possible to construct a closed loop in which the final event occurs before the initial event that started the chain, from the perspective of at least one valid observer. This is the light cone violation made explicit, translated from abstract algebra into a shape that can actually be drawn and visualized. The severity of this problem becomes even more apparent when considering how deeply embedded the light cone structure is in the rest of physics. It is not an isolated rule bolted onto relativity as an afterthought. It emerges directly from the geometry of space-time described by the theory, a geometry confirmed through decades of precision experiments, including measurements of time dilation in particle accelerators, the bending of light around massive objects, the behavior of global positioning satellites that must account for relativistic effects to maintain accuracy, and the observed timing of signals from distant pulsars and supernovae. Every one of these confirmations reinforces the same underlying structure, the same light cones, the same strict confinement of causal influence to within them. This raises a natural question that occupied physicists throughout the 20th century and continues to occupy them today. If the mathematics of relativity so clearly forbids faster-than-light causal influence, why does the subject remain a topic of ongoing research rather than a permanently closed case? Part of the answer lies in the difference between forbidding something within a well-tested framework and proving that no exceptions could ever exist under any circumstances, including circumstances involving physics not yet fully understood, such as the behavior of matter under extreme gravitational conditions, or the geometry of space-time in regions where general relativity, rather than special relativity, governs the rules. General relativity, Einstein's later and more comprehensive theory of gravity, describes space-time not as a fixed, flat backdrop, but as a dynamic structure that can curve, stretch, and even fold based on the distribution of mass and energy within it. This flexibility opens the door to solutions of Einstein's equations that produce far stranger structures than a simple light cone, including geometries where the light cones themselves tip over so far that paths through spacetime can loop back on themselves entirely. This possibility, that the shape of spacetime itself might permit a kind of causal loop without ever requiring an object to locally exceed the speed of light, represents one of the most intellectually serious challenges to the strict causality that special relativity seems to guarantee. Rather than an object accelerating past light speed and violating the light cone structure directly, general relativity raises the unsettling prospect that the light cones themselves, tilted and twisted by extreme gravitational fields, might conspire to produce a path through spacetime that returns to its own starting point, a scenario that does not require faster-than-light motion in any local sense, yet still threatens to produce the exact same causal contradictions that tachyons and superluminal signals were shown to create. Before exploring those exotic solutions in detail, it is worth pausing to examine exactly what kind of contradiction is at stake here, expressed not through the abstract language of light cones and reference frames, but through a scenario that has become one of the most famous thought experiments in the history of discussions about time, causality, and the philosophical weight of physical law, a scenario that strips away the mathematics and asks a single, disarmingly simple question about what would happen if someone could travel back far enough to interfere with the very chain of events that led to their own existence. Suppose a person somehow gained the ability to travel backward through time, not through any faster-than-light spacecraft, but through some theoretical mechanism permitted by the equations of general relativity. Suppose this person traveled back to a point before their own parents had met, and through some action, prevented that meeting from ever taking place. If the meeting never happens, the person is never born. But if the person is never born, they could never have existed to travel backward in time and prevent the meeting in the first place. This is the grandfather paradox, named for a common version of the thought experiment in which the time traveler prevents their own grandfather from surviving long enough to have children, and it represents one of the clearest illustrations of what physicists mean when they describe a violation of causal consistency. The grandfather paradox is often treated as a piece of philosophical wordplay, more suited to late-night conversation than serious physics, but the mathematics developed to describe faster-than-light travel in closed paths through spacetime shows that this paradox is not merely a linguistic trick. It is a structural feature that emerges whenever a physical system allows information or influence to travel into its own causal past. The tachyonic antitelephone discussed earlier is, in essence, a simplified signal-based version of the exact same problem. Instead of a person interfering with their grandparents, an observer interferes with the transmission of a message that was responsible for prompting their own reply. The chain of logic collapses in precisely the same way, regardless of whether the mechanism involves a physical body moving backward through time or a beam of faster-than-light particles carrying a coded signal. What makes this problem so significant for physics, rather than simply an interesting puzzle for philosophers, is that the equations describing relativity do not include any built-in safeguard against these paradoxes. The mathematics does not distinguish between a message that is used harmlessly and a message that is used to prevent its own transmission. Both scenarios are treated identically by the equations, right up until the moment a person tries to actually carry out the self-defeating action, at which point the paradox emerges not as a mathematical error, but as a logical contradiction layered on top of an otherwise perfectly valid solution to the equations of motion. This distinction matters enormously because it means the problem cannot simply be patched by refining the mathematics further. The equations are not broken. They are, in a sense, too permissive, allowing scenarios that lead to contradictions once an intelligent agent attempts to exploit them. Physicists studying this problem in the context of general relativity found themselves forced to take seriously something that had previously been dismissed as science fiction, namely the existence of exact mathematical solutions to Einstein's field equations that permit closed paths through spacetime, paths along which an object could, in principle, return to a point in its own past. These are known as closed time-like curves, and their discovery within legitimate solutions to general relativity's equations transformed the grandfather paradox from a thought experiment into a subject of serious theoretical physics. If such curves are mathematically permitted by the same equations that have been tested and confirmed through decades of astronomical observation, then the question of whether paradoxes like the grandfather paradox could actually occur in the real universe becomes a question that physics itself must answer, rather than a question that can be waved away as fiction. The first widely known example of such a solution was developed not long after Einstein published his general theory of relativity, when a mathematician and logician explored what would happen to the structure of spacetime within a universe that, unlike our own, was filled with a rotating distribution of matter rather than one that is simply expanding outward in every direction. Within this rotating universe, the geometry of spacetime becomes twisted in a very particular way, one that causes light cones at different points in space to tilt progressively as one moves outward from the center of rotation. Ordinarily, as established earlier, light cones remain oriented consistently, always pointing toward the future in a way that preserves a clear, agreed-upon direction of time for objects moving within them. But in this rotating solution, the tilting becomes so extreme at sufficient distance from the center that the light cones tip over entirely, opening a path along which an object moving only within its own local light cone, meaning an object never locally exceeding the speed of light in any small region of its journey, could nonetheless trace out a loop that returns to its exact starting point in both space and time. This is a crucial and often misunderstood detail. The paths described by this solution do not require anything to move faster than light at any point during the journey. Locally, every step along the path remains entirely within the bounds that special relativity permits. It is only when the entire path is considered as a whole, stretched across the twisted global geometry of this rotating universe, that the loop becomes apparent, closing back on its own beginning. This distinction reveals something important about how general relativity differs from special relativity in its treatment of causality. Special relativity assumes a flat, unchanging background structure for spacetime, one where light cones never tip beyond a certain angle and causal loops simply cannot form. General relativity abandons that assumption, allowing the structure of spacetime itself to be shaped by the distribution of mass, energy, and in this case, rotation, opening the mathematical door to geometries that special relativity's simpler framework would never permit. The rotating universe solution was, by its discoverer's own acknowledgement, not intended as a literal description of the actual universe humans inhabit. Observational evidence strongly suggests that the universe as a whole is not rotating in the way this solution requires, and no evidence has ever emerged supporting the idea that closed time-like curves exist naturally anywhere within it. But the value of the solution was never meant to be observational. Its value was to demonstrate, through rigorous mathematics rather than speculation, that Einstein's own equations, the same equations confirmed through gravitational lensing, the bending of starlight, the precise orbits of planets, and the detection of gravitational waves, do not inherently forbid the existence of closed time-like curves. If the universe does not contain them, it is not because the mathematics rules them out. It is because the actual physical conditions of our universe happen not to produce the specific configurations of mass, energy, and rotation required to generate them. This raised an urgent and uncomfortable question for physicists working in the field. If general relativity permits solutions containing closed time-like curves, and if some of those solutions might correspond to physically realizable configurations of matter and energy, such as rotating black holes, certain configurations of cosmic strings, or wormholes connecting distant regions of spacetime, then the grandfather paradox is not merely a philosophical curiosity confined to hypothetical, faster-than-light spacecraft. It becomes a live question about whether the actual laws governing our actual universe permit genuine causal paradoxes to occur under sufficiently extreme, though perhaps physically realizable, conditions. Several proposed responses to this problem emerged over subsequent decades, each attempting to reconcile the mathematical permissiveness of general relativity with the intuitive, deeply held expectation that causality should remain consistent throughout the universe. One influential approach argued that even if closed time-like curves exist as mathematical solutions, the process required to actually create one, whether through extreme rotation, exotic matter, or engineered wormholes, would always involve physical requirements so extreme that they could never actually be satisfied by any realistic configuration of matter and energy. Under this view, the mathematics permits closed time-like curves the way it permits many other exotic solutions that have no physical realization, such as configurations of matter with negative mass, existing on paper as valid equations but never appearing in the physical universe because no known process could actually assemble the required conditions. A different and more provocative approach accepted that closed time-like curves might indeed be physically possible under the right conditions, but proposed that the universe itself would prevent any actual paradox from occurring, not through any external enforcement mechanism, but through a kind of self-consistency built into the structure of physical law. Under this view, any attempt to use a closed time-like curve to alter the past would simply fail, not because of any barrier preventing the attempt, but because the events that occur would always, without exception, turn out to be consistent with everything that already happened, no matter how improbable the sequence of coincidences required to prevent the paradox might seem. This idea, formalized as a self-consistency principle, suggests that if someone traveled backward in time intending to prevent their grandfather from surviving to have children, something would always intervene, whether through mechanical failure, a change of heart, or sheer chance, ensuring that history remains unbroken. This proposal, while mathematically coherent, carries philosophical implications that many physicists find deeply uncomfortable, because it seems to strip away the free will typically assumed to govern human decision-making, replacing it with an underlying determinism so absolute that any decision leading toward paradox would always, without fail, be thwarted by circumstances beyond the person's control. Critics of the self-consistency principle argue that it resolves the mathematical paradox only by introducing an even stranger metaphysical commitment, one asserting that the universe actively conspires through whatever means necessary to prevent contradictions, even when those means require an implausible chain of coincidences stacking up precisely at the moment they are needed. Yet despite these philosophical difficulties, the self-consistency principle remains one of the most seriously considered frameworks for reconciling the existence of closed time-like curves within general relativity with the observed absence of causal paradoxes in our actual universe. It suggests that perhaps the light speed barrier explored earlier through tachyons and light cones is not the only safeguard nature employs to protect causality. Perhaps in situations where the geometry of space-time itself threatens to produce a paradox, the universe enforces consistency through the specific, if improbable, unfolding of events themselves, rather than through an absolute prohibition on the geometry that makes such loops mathematically possible in the first place. This possibility sets the stage for an even more direct examination of how physicists have approached constructing, at least on paper, mechanisms capable of producing exactly this kind of loop, beginning with an idea drawn not from cosmic rotation, but from a structure suggested by the very same equations that describe black holes, gravity, and the curvature of space-time around massive objects, a structure known as the wormhole. A wormhole begins as a mathematical curiosity buried inside the same equations that describe black holes, discovered not long after Einstein published his theory of general relativity, when researchers examining the exact solution, describing a spherically symmetric mass, noticed something unexpected embedded within the geometry. The solution did not simply describe a single region of curved spacetime surrounding a massive object. Under certain interpretations, it appeared to describe two separate regions of spacetime, connected through a narrow throat, a kind of bridge linking what would otherwise be two entirely separate universes or two widely separated regions of the same universe. This structure became known first as an Einstein-Rosen bridge, named after the physicists who examined its mathematical properties in detail, and later became more widely known by the more evocative term wormhole, a name that captures the intuitive image of a shortcut burrowing through the fabric of space-time rather than traveling across its surface. The appeal of this idea to anyone contemplating faster-than-light travel is immediate and obvious. If two distant points in space could be connected by a short throat running through some additional dimension of geometry, then an object passing through that throat might travel between 2 points separated by enormous ordinary distances without ever locally exceeding the speed of light at any point during its journey. This distinction is worth dwelling on carefully because it represents one of the most important conceptual shifts in the entire discussion of faster-than-light travel. A wormhole does not propose that an object accelerates to a velocity greater than light speed. Instead, it proposes that the distance the object needs to travel is dramatically reduced by the geometry of space-time itself, folding the space between 2 points so that they become, in effect, much closer together than they would appear when measured along the conventional unfolded route. An analogy commonly used to illustrate this idea imagines a sheet of paper representing two-dimensional space with 2 points marked at opposite ends. Traveling from one point to the other across the flat sheet requires crossing its entire length, but if the sheet is folded so that the 2 points touch, or nearly touch, an object could pass directly from one point to the other by punching through the small gap between the folded layers, traveling a much shorter distance than the flat, unfolded sheet would suggest. This analogy, while useful for building intuition, understates the mathematical complexity involved in actually constructing a stable, traversable wormhole using the equations of general relativity. The original Einstein-Rosen bridge solution, despite its intriguing geometry, turned out to be unstable in a very specific and physically important way. Detailed analysis showed that the throat connecting the two regions of spacetime would pinch off and collapse extraordinarily quickly, far too quickly for any object, even one moving at the speed of light itself, to pass through before the connection sealed shut. In its original form, the wormhole solution was less like a stable tunnel and more like a bridge that collapses the instant weight is placed upon it, a mathematically valid but practically useless structure for the purposes of travel. The situation changed substantially decades later, when physicists specifically investigating the requirements for a traversable wormhole, meaning one stable enough for an object to actually pass through and survive the journey, worked out what conditions would need to be satisfied to prevent the throat from collapsing. Their analysis revealed that stabilizing a wormhole's throat would require the presence of a very particular and exotic form of matter or energy, one possessing what is called negative energy density. This is a genuinely strange requirement because virtually all matter and energy observed anywhere in the universe possesses positive energy density, meaning it exerts an attractive gravitational pull that would tend to cause the wormhole's throat to collapse further rather than propping it open. Negative energy density, by contrast, would exert an effectively repulsive gravitational influence, counteracting the collapse and holding the throat open long enough for something to pass through. The requirement for negative energy is not simply an inconvenient technical detail. It touches on one of the more exotic corners of physics, an area where quantum theory and general relativity intersect in ways that remain only partially understood. Certain quantum phenomena, such as the Casimir effect, in which two closely spaced, uncharged conducting plates experience a measurable force due to fluctuations in the quantum vacuum between them, have been experimentally confirmed to involve regions of effectively negative energy density, at least in a localized and extremely small-scale sense. This provides a proof of concept that negative energy density is not forbidden by physics in an absolute sense, but the amount of negative energy required to stabilize a wormhole throat large enough and stable enough to allow a spacecraft or even a single particle carrying useful information to pass through safely would need to be vastly larger in magnitude and would need to be sustained over a much larger region than anything the Casimir effect or any other known quantum phenomenon has ever been observed to produce. This gap between the small laboratory-confirmed instances of negative energy density and the enormous sustained quantities that traversable wormhole models require represents one of the most significant obstacles standing between wormholes as a mathematically valid solution and wormholes as a physically realizable structure. Some physicists have proposed that quantum gravity, a still incomplete theory attempting to unify general relativity with quantum mechanics, might eventually reveal mechanisms capable of producing the necessary negative energy densities under specific engineered conditions. Others remain skeptical that nature permits negative energy densities to exist at the scale and duration required, suspecting instead that some deeper physical principle, not yet fully understood, imposes a strict limit on how much negative energy can exist in any given region of spacetime for any sustained length of time, a limit sometimes referred to informally as a quantum inequality. Setting aside for a moment the formidable question of whether traversable wormholes could ever actually be constructed, it is worth examining what would happen to causality if such a structure did exist and could be used for travel. Here, the story returns directly to the paradoxes explored earlier, because a sufficiently engineered wormhole does not merely offer a shortcut through space. Under certain configurations, it can be transformed into a shortcut through time as well, producing precisely the kind of closed time-like curve discussed in the context of the rotating universe solution, but through a mechanism that seems, at least superficially, far more physically plausible than a hypothetical rotating cosmos. The mechanism works as follows. Suppose one mouth of a wormhole is transported away from the other mouth at a velocity approaching the speed of light, perhaps aboard a fast-moving spacecraft, while the second mouth remains stationary. Because of the time dilation effects discussed earlier, time would pass more slowly for the traveling mouth relative to the stationary one. After the traveling mouth returns or simply continues moving for a sufficient period, a significant discrepancy would accumulate between the amount of time that has elapsed at each end of the wormhole. An object entering the wormhole from the stationary mouth would then emerge from the traveling mouth not just at a different location in space, but at an earlier point in time relative to the stationary mouth's frame of reference, effectively transforming the wormhole into a time machine connecting two different moments in history rather than simply two different points in space. This proposal, worked out in careful mathematical detail by physicists studying the implications of traversable wormhole solutions, demonstrates that the same structure proposed to solve the problem of faster-than-light travel across vast distances could, under a fairly straightforward set of additional conditions, also produce the exact grandfather paradox scenario described earlier, but through a mechanism far more concrete than an abstract rotating universe that observational evidence suggests does not describe our own cosmos. If traversable wormholes are physically possible, and if they can be manipulated in the manner described to create a time differential between their two mouths, then closed time-like curves would not require any exotic cosmological model at all. They could, in principle, be engineered directly, using nothing more exotic than the same wormhole physics already required to explain faster-than-light travel across space. This connection between spatial shortcuts and temporal shortcuts reveals something important about the deep structure of the problem being investigated throughout this analysis. Faster-than-light travel and time travel are not two separate, unrelated speculative topics that happen to share some superficial similarities. Within the framework of relativity, they are two expressions of the same underlying mathematical structure. Any mechanism capable of moving an object between 2 points in spacetime faster than light could travel. The ordinary route can, under sufficiently general conditions, be reconfigured to move an object between 2 points in a way that violates the ordinary, agreed-upon ordering of cause and effect. This is not a coincidence or an unfortunate side effect layered onto an otherwise sound idea. It follows directly and unavoidably from the way relativity ties space, time, and causal structure together into a single unified geometric framework. Confronted with this deep connection, physicists studying traversable wormholes and their potential use as time machines proposed several possible resolutions, echoing many of the same responses developed earlier in the context of tachyons and closed time-like curves in rotating universes. Some argued that the extreme physical requirements involved in creating and stabilizing a wormhole, particularly the enormous and sustained negative energy densities required, would always prove impossible to satisfy in practice, serving as a kind of natural safeguard that prevents time machines from ever actually being constructed, regardless of what the idealized mathematics might suggest. Others pointed to the self-consistency principle discussed previously, suggesting that even if a wormhole time machine could somehow be built, any attempt to use it to alter the past would simply fail, thwarted by whatever improbable chain of events proves necessary to preserve a single, unbroken, self-consistent history. Still others proposed a third possibility, one that would come to be known as chronology protection, suggesting that the universe possesses an active physical mechanism rooted in the behavior of quantum fields near the threshold of closed time-like curve formation that would prevent such curves from ever actually forming in the first place, regardless of how the classical, non-quantum equations of general relativity might describe the geometry. This proposal shifted the investigation away from purely classical general relativity and into the more uncertain, still developing territory where quantum mechanics and gravity intersect, suggesting that the final word on whether faster-than-light travel, wormhole time machines, and their associated paradoxes are truly possible may not come from Einstein's equations alone, but from a more complete theory of quantum gravity that physicists have not yet fully developed. Before examining chronology protection in detail, however, it is worth turning to a phenomenon that, at first glance, seems to violate the light-speed barrier directly, observed not in a laboratory or a hypothetical thought experiment, but in the sky itself, streaming outward from some of the most energetic objects known to exist in the universe. In the 1970s, astronomers studying radio observations of certain distant galaxies noticed something that appeared, at first glance, to violate everything just established about the impossibility of faster-than-light motion. Streams of material, ejected from the cores of these galaxies, seem to be moving across the sky at speeds several times greater than the speed of light, based on careful measurements of how far the material appeared to travel between successive observations, divided by the time elapsed between those observations. If taken at face value, these measurements suggested that jets of plasma erupting from distant galactic nuclei were somehow achieving velocities that no particle accelerator on Earth, no laboratory experiment, and no theoretical framework had ever come close to permitting. This phenomenon became known as superluminal motion, and its resolution offers one of the clearest illustrations of how easily faster-than-light appearances can arise from entirely mundane physics, once the geometry of the situation is properly understood. The objects responsible for these observations are called active galactic nuclei, extraordinarily energetic regions at the centers of certain galaxies, believed to be powered by supermassive black holes, accreting surrounding matter at tremendous rates. As matter spirals inward toward these black holes, a portion of it is redirected outward in narrow, highly collimated jets, launched perpendicular to the swirling disk of infalling material through mechanisms that remain an active area of research, but that clearly involve powerful magnetic fields threading through the superheated plasma near the black hole. These jets can extend for distances comparable to the size of the host galaxy itself, and the material within them moves at velocities that, while never actually exceeding the speed of light, come remarkably close to it, often reaching more than 99% of light speed. The illusion of superluminal motion arises from a specific geometric alignment between the direction the jet is traveling and the direction toward the observer on Earth. When a jet happens to be oriented nearly along the line of sight toward Earth, meaning the material is moving almost directly toward the observer rather than across the observer's field of view, a subtle but important effect comes into play. Because the material in the jet is moving at a velocity extremely close to the speed of light, and because it is moving nearly directly toward the observer, the light emitted by the jet at a later point in its journey has only a slightly greater distance to travel to reach the observer than light emitted at an earlier point. This means the time interval between when the observer receives light from two different points along the jet's path is compressed compared to the actual time interval, measured in the observer's own reference frame, that the jet took to travel between those 2 points. To understand this concretely, Imagine a jet emitting a pulse of light at one moment, then traveling for a certain period of time before emitting a second pulse from a point much closer to Earth, since it has been moving nearly directly toward the observer during the interval between pulses. Because the jet was already moving at a velocity close to the speed of light during this interval, and because the second pulse has less distance to cross to reach Earth than the first, the second pulse arrives at the observer's telescope only a short time after the first, even though a much longer period of time actually elapsed in the jet's own frame of motion between the emission of the two pulses. When astronomers then calculate the jet's apparent speed by dividing the observed transverse distance the material appears to have covered by the compressed time interval between the arrival of the two pulses, the result can produce an apparent velocity that appears to exceed the speed of light, sometimes dramatically so, even though the actual physical velocity of the material never came close to that threshold. This effect, known as superluminal motion in the observational sense, is not a violation of relativity at all. It is, in fact, a direct and elegant confirmation of relativity's predictions, since the specific mathematical relationship between the true velocity of the jet, the angle between its direction of motion and the observer's line of sight, and the resulting apparent velocity can be calculated precisely using standard relativistic formulas, and the results match observations with remarkable accuracy. Astronomers have used this relationship in reverse, taking the observed apparent velocities of numerous jets and calculating the true velocities and orientation angles that would be required to produce them, arriving at values entirely consistent with independent measurements of black hole jet velocities obtained through other methods such as analyzing the Doppler shifting of light emitted by the approaching and receding portions of the jet material. This resolution carries an important lesson that recurs throughout the broader investigation of faster-than-light phenomena. Appearances of superluminal motion, whether observed in distant galactic jets or proposed in various theoretical contexts, must always be carefully examined to determine whether they represent genuine, faster-than-light travel of matter or information, or whether they arise instead from geometric or observational effects that create an illusion of exceeding the light barrier without any actual violation taking place. The universe, it turns out, offers several distinct mechanisms capable of producing apparent faster-than-light behavior, and distinguishing between genuine violations and geometric illusions requires careful quantitative analysis rather than surface-level observation. A related, though conceptually distinct category of apparent faster-than-light motion arises not from the geometry of an observer's perspective, but from the physical behavior of light itself as it passes through different materials. When light travels through a vacuum, it moves at the universal constant velocity that plays such a central role throughout relativity. But when light passes through a transparent medium, such as water, glass, or air, it interacts with the atoms composing that medium in a way that effectively slows its propagation speed below the vacuum value. This slowed speed is described by a quantity called the refractive index, which varies depending on the specific material and the wavelength of light passing through it. This distinction between the speed of light in a vacuum and the reduced speed of light within a material medium opens up an intriguing possibility. While nothing can exceed the speed of light in a vacuum, which represents the universal constant embedded in the fundamental structure of relativity, it is entirely possible for a charged particle to travel through a medium such as water at a velocity greater than the reduced speed of light within that particular medium without ever approaching, let alone exceeding, the vacuum speed of light that relativity actually forbids. When this occurs, the charged particle produces a distinctive cone of light, analogous in its geometric formation to the sonic boom produced by an aircraft exceeding the speed of sound in air. This optical phenomenon, named Cherenkov radiation after the physicist who first rigorously characterized it, produces a faint blue glow that has become one of the most visually striking and scientifically useful phenomena in experimental particle physics. Cherenkov radiation appears prominently in the water surrounding nuclear reactor cores, where high-energy particles emitted during radioactive decay processes travel through the surrounding water at velocities exceeding the local speed of light in water, despite remaining far below the vacuum speed of light. The characteristic blue glow visible in photographs of reactor cores submerged in water pools is a direct visual manifestation of this effect, and it provides a striking, real-world demonstration that particles routinely travel faster than light within a specific medium, without violating any principle of relativity whatsoever. Physicists studying cosmic rays and neutrino interactions have exploited this same phenomenon deliberately, constructing massive detectors filled with pure water or ice, designed specifically to capture the faint Cherenkov light produced when high-energy particles pass through, using the characteristics of that light to reconstruct the energy, direction, and identity of the particles responsible. It is worth pausing to emphasize precisely why Cherenkov radiation does not represent a violation of relativity's speed limit, despite frequently being described in popular science communication using language that implies particles are moving faster than light in some absolute sense. The speed limit imposed by relativity applies specifically and exclusively to the speed of light in a vacuum, a fundamental constant tied to the fabric of space-time itself. The reduced speed of light within a material medium is not a fundamental constant of nature. It is a consequence of light's electromagnetic interaction with the charged particles composing that particular medium, an interaction that effectively delays light's progress compared to its unimpeded vacuum velocity. A charged particle exceeding this reduced medium-dependent speed is not exceeding any universal limit. It is simply outpacing a locally slowed version of light, in the same way a jet aircraft can exceed the speed of sound in air without exceeding any universal cosmic speed limit related to sound, since sound's propagation speed is itself dependent on the specific medium through which it travels. These two phenomena, superluminal jet motion and Cherenkov radiation, illustrate an important pattern that recurs whenever faster-than-light claims surface in scientific or popular discourse. Careful examination consistently reveals that apparent violations of the light-speed barrier arise from specific, well-understood physical mechanisms, whether geometric projection effects involving an observer's line of sight, or the distinction between light's vacuum speed and its reduced speed within material media, rather than from any genuine breach of the fundamental limit imposed by relativity. This pattern would be tested again, and far more dramatically, in the early 21st century, when a major international physics collaboration announced experimental results appearing to show subatomic particles traveling faster than light not within any medium and not subject to any geometric illusion, but across empty space, in results that briefly seemed to threaten one of the best confirmed principles in all of physics, before an intensive investigation revealed something that would become a defining case study in scientific rigor, caution, and the importance of ruling out mundane explanations before announcing an extraordinary discovery. In September of 2011, a collaboration of physicists working on an experiment named OPERA, designed to study neutrinos produced at a particle accelerator facility and detected at a laboratory located deep underground, several hundred kilometers away, announced a result that immediately captured attention across the scientific world and beyond it. Their measurements appeared to show that neutrinos, tiny, nearly massless subatomic particles capable of passing through ordinary matter with almost no interaction whatsoever, had traveled the distance between the two facilities in slightly less time than light would have required to cover the same distance through a vacuum. The discrepancy was small, amounting to a difference of roughly 60 nanoseconds, but the distance involved and the precision of the timing equipment used meant that this small discrepancy translated into an apparent velocity for the neutrinos, exceeding the speed of light by a tiny but statistically significant margin. The announcement was met with immediate and intense scrutiny from the broader physics community, precisely because the implications, if confirmed, would have been staggering. A genuine measurement of faster-than-light travel by ordinary matter, achieved not through geometric illusion, not through the reduced speed of light within a material medium, but through actual motion across empty space, would have directly contradicted one of the most thoroughly tested principles in the history of physics, a principle underlying not just relativity itself, but the entire structure of modern particle physics, nuclear physics, and cosmology. The researchers involved in the OPERA collaboration were themselves notably cautious in how they presented their findings, explicitly stating that they had spent months attempting to identify any systematic error that might explain the anomalous result before deciding to release it publicly. And they explicitly invited independent scrutiny and further investigation rather than claiming to have discovered a violation of relativity. This caution proved well-founded. Over the following months, physicists, both within the Opera collaboration and from other research groups around the world, subjected the experiment's methodology to intense examination, focusing particularly on two extraordinarily delicate technical requirements involved in the measurement. The first requirement involved knowing, with extreme precision, the exact distance between the point where the neutrinos were produced and the point where they were detected, a distance that needed to be measured to an accuracy of centimeters across a path spanning hundreds of kilometers, much of it running through solid rock beneath the Earth's surface. The second requirement involved synchronizing the clocks used to measure the departure and arrival times of the neutrinos with comparable precision, a task complicated by the fact that the two facilities were located in different countries, connected by complex chains of timing equipment, satellite-based positioning signals, and fiber optic cables, any one of which could introduce a subtle timing error if not accounted for with complete accuracy. The eventual resolution of the anomaly, announced in early 2012, traced the discrepancy to two specific technical issues within the experiment's timing apparatus. One issue involved a fiber optic cable connector that had not been fully seated, introducing a small but significant delay into the timing signal used to synchronize the experiment's clocks. Once this connector was properly seated and the timing recalibrated, part of the discrepancy disappeared. A second, partially compensating issue involved an oscillator used in the timing system that was found to be running at a slightly different rate than expected, introducing an additional timing error in the opposite direction. When both of these technical issues were properly accounted for, the neutrino's measured velocity fell back into complete agreement with the speed of light, consistent with every other measurement of neutrino behavior obtained before and since, and consistent with the vast body of experimental evidence supporting special relativity's speed limit. The Opera episode holds significant value for this broader investigation, not because it revealed anything new about the physics of faster-than-light travel, but because it demonstrated in real time and under intense public scrutiny exactly how the scientific community handles an apparent violation of one of its most fundamental and thoroughly tested principles. Rather than either dismissing the result outright without investigation or embracing it uncritically as a revolutionary discovery, the physics community subjected the claim to the kind of rigorous, methodical scrutiny that precision measurements of this significance demand, ultimately tracing the anomaly to specific, identifiable, and mundane technical errors rather than any genuine new physics. This pattern, extraordinary claims triggering extraordinarily careful verification, reflects a core principle of how science approaches any result that appears to contradict a well-established theoretical framework, and it stands in useful contrast to the geometric illusions responsible for superluminal jet motion and the medium-dependent effects responsible for Cherenkov radiation, since the Opera anomaly arose from neither of those causes, but from something far more mundane, an instrumental error in an extraordinarily delicate measurement. Having examined superluminal jets, Cherenkov radiation, and the Opera neutrino anomaly, each representing a case where apparent faster-than-light motion dissolved under careful analysis into either geometric illusion, medium-dependent effects, or straightforward measurement error, it becomes necessary to turn to a phenomenon that occupies a genuinely different category, one that has generated persistent public confusion and remains, even among physicists, a subject requiring careful and precise language to describe accurately. This phenomenon is quantum entanglement, a property of certain quantum systems that Einstein himself famously found deeply unsettling, and one frequently, though incorrectly, described in popular science communication as enabling faster-than-light communication between distant particles. Quantum entanglement arises when two or more particles are produced or interact in such a way that their quantum states become correlated in a manner that cannot be described by treating each particle as possessing independent, definite properties prior to measurement. A commonly discussed example involves a pair of particles produced with correlated quantum spin properties, such that measuring the spin of one particle along a particular axis instantaneously determines what the corresponding measurement of the other particle's spin would yield, even if the two particles have since traveled to locations separated by enormous distances, far too great for any signal traveling at the speed of light to have passed between them in the time available before both measurements are completed. This instantaneous correlation is precisely what led Einstein, along with physicists Boris Podolsky and Nathan Rosen, to formulate what became known as the Einstein-Podolsky-Rosen paradox in 1935, arguing that this apparent instantaneous influence between distant particles suggested that quantum mechanics, as formulated at the time, must be an incomplete description of physical reality, since it seemed to require what Einstein memorably described as spooky action at a distance, a phrase that has persisted in popular discussions of entanglement ever since, despite being originally intended as a criticism rather than an endorsement of the phenomenon's implications. Einstein and his colleagues proposed that some deeper, as yet undiscovered set of hidden variables must actually determine each particle's properties from the moment of their creation, eliminating the need for any instantaneous influence and restoring a picture of reality in which distant objects cannot affect each other without some signal traveling between them. This question, whether quantum entanglement reflects genuine instantaneous influence between distant particles or merely reveals pre-existing hidden properties established at the moment of the particle's creation, remained a subject of theoretical debate for nearly 3 decades, until a physicist named John Stuart Bell developed a mathematical framework capable of actually testing the question experimentally, rather than leaving it as a matter of philosophical interpretation. Bell's theorem established a specific mathematical inequality, that any theory based on local hidden variables, meaning a theory in which each particle's properties are fixed in advance and no influence travels between them faster than light, would necessarily satisfy. Quantum mechanics, by contrast, predicted that certain measurements on entangled particles would violate this inequality, producing correlations stronger than any local hidden variable theory could account for. Beginning in the 1970s and continuing with increasing precision and sophistication through subsequent decades, physicists conducted a series of increasingly rigorous experiments designed to test Bell's inequality directly, using entangled photons separated by progressively greater distances and employing increasingly stringent methods to rule out any conceivable way that ordinary, light-speed-limited signals could account for the observed correlations. These experiments consistently and decisively confirmed the predictions of quantum mechanics, violating Bell's inequality by margins that local hidden variable theories simply cannot explain, a result recognized with the award of the Nobel Prize in Physics in 2022 to 3 physicists whose experimental work had been central to closing the remaining loopholes in these tests over the preceding decades. This experimental confirmation might seem, at first glance, to vindicate exactly the kind of instantaneous, faster-than-light influence that Einstein found so troubling, and popular science writing frequently describes entanglement in precisely these terms, suggesting that measuring one particle somehow sends information instantaneously to its entangled partner regardless of distance. But this description, while capturing something true about the strangeness of entangled correlations, fundamentally misrepresents what entanglement actually allows. And understanding exactly where this common description goes wrong reveals one of the most subtle and important distinctions in the entire discussion of faster-than-light phenomena, a distinction that separates entanglement's genuine strangeness from any actual violation of relativity's causal structure, and one that requires careful examination of precisely what information, if any, entanglement allows to pass between distant observers. The crucial detail that popular descriptions of quantum entanglement routinely omit is that no usable information can actually be transmitted from one entangled particle to another through the act of measurement, and this omission is not a minor technical footnote. It is the entire resolution to the apparent conflict between entanglement and relativity. When a physicist measures the spin of one particle in an entangled pair, the outcome of that measurement is fundamentally random. There is no way to control or predict in advance which specific result the measurement will produce. The particle might be measured as spin up, or it might be measured as spin down, with the specific outcome determined only at the moment of measurement, not before. This randomness is not a limitation of current measurement technology. It is a fundamental feature of quantum mechanics itself, confirmed repeatedly through decades of experimentation. Because the outcome at the first location is genuinely random and uncontrollable, an observer at the second location, holding the entangled partner particle, cannot extract any meaningful information from measuring their own particle alone. If they measure their particle and obtain a result, that result will indeed be correlated with whatever result was obtained at the first location, but the second observer has no way of knowing from their measurement alone whether the first measurement has even taken place yet, nor any way of distinguishing a scenario in which the correlation was produced by genuine entanglement from a scenario in which the two particles' properties were simply determined randomly and independently at the moment of their creation without any entanglement or correlation at all. The correlation only becomes apparent and only becomes useful in any sense when the results from both measurements are eventually compared, and this comparison absolutely requires a conventional signal, traveling at or below the speed of light to carry the results from one location to the other. This is the resolution that keeps entanglement fully consistent with relativity's causal structure, and it is worth stating plainly and precisely. Entanglement produces correlations between distant measurement outcomes that cannot be explained by any theory involving only local, predetermined hidden variables, exactly as Bell's theorem and its subsequent experimental confirmations demonstrated. But entanglement does not allow any controllable information, no message, no signal, no meaningful content of any kind, to be transmitted from one location to the other faster than light. The random nature of each individual measurement outcome ensures that no one holding just one particle from an entangled pair can use that particle alone to send a chosen message to someone holding the other particle. Confirming the correlation, and thereby confirming that the particles were indeed entangled, requires classical communication between the two locations, communication that is itself limited to the speed of light exactly as relativity demands. This distinction between correlation and communication resolves what might otherwise appear to be a direct contradiction between quantum mechanics and relativity, and it illustrates a principle that recurs throughout serious theoretical physics whenever faster-than-light claims are examined closely. The question that actually matters for the purposes of causality and the light cone structure explored earlier is never simply whether some effect appears to happen instantaneously across a distance. The question that matters is whether that effect can be used to transmit controllable, meaningful information from one point to another faster than light could carry the same information along the conventional route. Superluminal jets fail this test because the jets never actually move faster than light in any local sense, only appearing to do so due to geometric projection effects. Cherenkov radiation fails this test because it involves light's reduced speed within a material medium, not the fundamental vacuum speed limit that relativity actually protects. And quantum entanglement fails this test because the correlations it produces, however strange and however thoroughly confirmed by rigorous experimentation, cannot be harnessed to send an actual message without resorting to conventional, light-speed-limited communication to compare results. Physicists sometimes summarize this principle using the phrase no signaling, referring to a set of theorems proven directly from the mathematical structure of quantum mechanics, demonstrating that entanglement, regardless of how it might eventually be exploited by future technology not yet imagined, can never be used to violate this fundamental restriction on faster-than-light communication. These theorems are not merely empirical observations awaiting a future exception. They are proven mathematical consequences of quantum mechanics' own internal structure, meaning that violating them would require quantum mechanics itself to be wrong in a way that decades of extraordinarily precise experimentation have found no evidence for whatsoever. This resolution of the entanglement puzzle brings the investigation to another category of apparent, faster-than-light phenomena, one that arises not from subatomic particles or laboratory experiments, but from the largest scale structure of the universe itself, observed through the systematic retreat of distant galaxies from our own, a retreat that, at sufficiently great distances, proceeds at a rate that genuinely does exceed the speed of light, and yet, remarkably, does so without violating relativity in any way whatsoever, for reasons that require understanding exactly what is actually expanding when astronomers describe the universe as growing larger over time. Observations conducted throughout the 20th century, beginning with the work of astronomer Edwin Hubble, revealed that distant galaxies are systematically moving away from our own galaxy, and that the velocity of this apparent recession increases in direct proportion to a galaxy's distance from us. This relationship, now known as Hubble's law, initially seemed to suggest that our galaxy occupies some special central position in the universe, with everything else fleeing outward from it. But subsequent theoretical and observational work revealed a very different and considerably more elegant picture, one in which no galaxy occupies any privileged central position at all. Instead, the space between galaxies is itself expanding uniformly throughout the universe, meaning that an observer located in any galaxy, anywhere in the cosmos, would observe the same pattern, with every sufficiently distant galaxy appearing to recede from them, and with more distant galaxies appearing to recede more rapidly than nearer ones. This distinction between galaxies moving through space and space itself expanding between galaxies is not merely a semantic preference among cosmologists. It represents a fundamentally different physical picture, one with direct and important implications for the question of faster-than-light motion. When Hubble's law is extrapolated to sufficiently great distances, it predicts that galaxies located beyond a certain distance from any given observer will appear to recede at velocities exceeding the speed of light. This is not a theoretical curiosity confined to the distant future or the extreme edges of observational capability. Current measurements of the universe's expansion rate indicate that galaxies located beyond a specific boundary, calculated from the best available cosmological data, are indeed receding from us at velocities greater than light speed at this very moment. This might seem to represent exactly the kind of faster-than-light violation that special relativity forbids, but the resolution lies in recognizing that special relativity's speed limit applies specifically to the motion of objects through space, not to the expansion of space itself. A galaxy receding from an observer due to cosmic expansion is not, in any meaningful sense, moving through the space immediately surrounding it at a velocity approaching or exceeding light speed. Locally, in the immediate vicinity of that galaxy, everything remains entirely consistent with special relativity, with no object moving through its local neighborhood of space faster than light. The recession velocity arises instead from the cumulative effect of space itself expanding across the enormous distance separating the galaxy from the observer, with each small increment of space between them stretching slightly, and the cumulative stretching across billions of light years of intervening space, adding up to a recession velocity that exceeds light speed, even though no single local region of space is doing anything that violates relativity's restrictions. An analogy frequently used to illustrate this distinction imagines a large balloon with dots painted on its surface, representing galaxies, being steadily inflated. As the balloon expands, every dot moves away from every other dot, with dots that are farther apart on the balloon's surface moving apart from each other more rapidly than dots that are closer together, simply because there is more expanding surface area between them, contributing to their mutual separation. No individual dot is moving across the balloon's surface in any meaningful sense. Each dot remains essentially fixed relative to its immediate surroundings on the balloon's fabric. It is the fabric itself, stretching uniformly everywhere, that produces the appearance of dots moving apart, with the total separation rate between any two dots depending on how much expanding fabric lies between them. This analogy, like all analogies used to describe cosmic expansion, has limitations and should not be stretched too literally, but it captures the essential physical distinction correctly. The recession velocity of a distant galaxy is not a velocity in the same sense that special relativity's speed limit addresses. It is a rate of separation produced by the cumulative expansion of space itself, a phenomenon governed not by special relativity, which describes motion through a fixed space-time background, but by general relativity, which describes the dynamic behavior of spacetime's own geometry, including its capacity to expand, contract, or curve based on the distribution of matter and energy within it. Crucially, and consistently with everything established earlier about causality and information transfer, this cosmic expansion does not allow for the transmission of any information faster than light. A galaxy receding from us at a velocity exceeding light speed cannot send us a signal, because any signal it emits traveling at the speed of light through its own local region of space will find itself perpetually outpaced by the expanding space it must cross to reach us, if the galaxy lies beyond a specific boundary known as the cosmic event horizon. This horizon marks the boundary beyond which light emitted today will never be able to reach an observer on Earth, regardless of how much time is allowed to pass, precisely because the space between the source and the observer is expanding at a rate that outpaces light's ability to close the gap. This is a genuinely faster-than-light phenomenon, arising directly from the equations of general relativity applied to the large-scale structure of the universe. And yet it produces no causality violation whatsoever, no closed time-like curves, no possibility of information arriving before it is sent, precisely because it does not involve any object or signal moving through its own local spacetime faster than light. It involves spacetime itself changing shape on a scale so vast that ordinary intuitions about speed and distance simply cease to apply in any straightforward way. Having now examined the full range of ways faster-than-light appearances can arise without genuine causality violation, from geometric illusions in distant jets, to medium-dependent effects in particle physics, to statistical measurement errors in delicate experiments, to the subtle but crucial distinction between correlation and communication in quantum entanglement, to the expansion of space itself outpacing light across cosmic distances, the investigation returns to the genuinely troubling cases explored earlier: the tachyonic anti-telephone, the rotating universe's closed time-like curves, and the wormhole time machine, each of which does appear to threaten actual causality violation if realized. This return raises a pointed question that theoretical physicists have pursued with increasing sophistication in recent decades. If classical general relativity permits these paradox-generating solutions, does a more complete theory of physics, one that properly incorporates the principles of quantum mechanics into the description of gravity and spacetime, ultimately forbid them after all, closing the loopholes that classical relativity leaves disturbingly open? This question found its most influential formulation in the work of physicist Stephen Hawking, who in 1992 proposed what he called the chronology protection conjecture, a hypothesis suggesting that the laws of physics, taken as a complete whole rather than considered piece by piece, actively conspire to prevent the formation of closed time-like curves, ensuring that the paradox-generating scenarios explored earlier, however mathematically valid they might appear within classical general relativity alone, could never actually be realized in a universe that also obeys the principles of quantum mechanics. Hawking's proposal was not presented as a proven theorem, but rather as a conjecture grounded in specific physical reasoning that drew on the behavior of quantum fields in the extreme, warped regions of spacetime where closed time-like curves would need to form. To understand the basis for this conjecture, it helps to recall a detail mentioned earlier regarding the traversable wormhole time machine, in which one mouth of the wormhole is transported at high velocity relative to the other, gradually building up a time differential between them, until eventually an object entering one mouth would emerge from the other at an earlier point in time, creating exactly the kind of closed time-like curve responsible for the grandfather paradox. Hawking and other physicists studying this scenario recognize that the moment just before such a configuration becomes capable of producing closed time-like curves represents a genuinely special and physically significant threshold, one where the behavior of quantum fields within the wormhole's throat needs to be examined with extreme care, since classical general relativity alone cannot fully describe what happens to matter and energy under such extreme geometric conditions. When physicists perform this analysis, calculating how quantum fields would behave as a wormhole or any other spacetime geometry approach the threshold of generating a closed time-like curve, they found a striking and suggestive result. As the geometry approaches the critical configuration required to create a closed time-like curve, the calculated energy density of quantum vacuum fluctuations within that region appears to increase dramatically, in many calculated scenarios growing without bound, approaching what physicists describe as a divergence. This divergence in energy density, if it genuinely and universally occurs in any real physical situation approaching closed time-like curve formation, would produce such an enormous concentration of energy that it would catastrophically disrupt the very geometry required to produce the closed time-like curve in the first place, effectively sealing off the pathway before it could ever become traversable. Under this interpretation, quantum field effects would act as a kind of automatic circuit breaker, triggering precisely at the moment a paradox-generating configuration threatens to form and destroying that configuration before any paradox could actually occur. This proposed mechanism carries an appealing elegance because it does not require inventing any new law of physics, nor does it require introducing the somewhat philosophically uncomfortable self-consistency principle discussed earlier, in which the universe must always conspire through whatever improbable chain of events proves necessary to prevent any actual paradox from unfolding. Instead, chronology protection suggests that ordinary, well-established quantum field theory, applied carefully to the specific and extreme geometric conditions required for closed time-like curve formation, naturally and automatically produces effects that prevent those conditions from ever being fully realized, closing the loophole not through narrative coincidence, but through calculable physics. However, the chronology protection conjecture remains, even decades after Hawking first proposed it, a conjecture rather than a settled theorem, and the reasons for this lingering uncertainty reveal a great deal about the current limits of theoretical physics. The calculations suggesting that quantum vacuum energy diverges as a space-time geometry approaches closed time-like curve formation have been performed using a framework known as semi-classical gravity, an approach that treats matter and energy according to the rules of quantum field theory, while continuing to treat the geometry of space-time itself according to the classical, non-quantum equations of general relativity. This hybrid approach has proven extraordinarily useful throughout theoretical physics, producing accurate predictions in a wide range of situations, including the celebrated prediction that black holes should slowly emit radiation and eventually evaporate, a result also derived by Hawking using this same semi-classical framework. But semi-classical gravity is understood by physicists to be an approximation, one that should break down precisely in the most extreme regimes where the curvature of space-time becomes so severe that quantum effects on the geometry itself, not merely on the matter and energy moving through that geometry, become significant and can no longer be safely ignored. This creates a frustrating and somewhat ironic situation for anyone hoping to settle the question of chronology protection definitively. The very conditions under which closed time-like curves would actually form, conditions involving extreme space-time curvature at the threshold of paradox-generating geometry, are precisely the conditions under which the semi-classical approximation used to calculate the diverging vacuum energy becomes least reliable. A fully rigorous resolution of the chronology protection conjecture would seem to require a complete theory of quantum gravity, one that properly quantizes space-time geometry itself, rather than treating it as a fixed classical background upon which quantum fields merely happen to exist. No such complete theory of quantum gravity currently exists, despite decades of intensive theoretical effort pursued through multiple competing approaches, including string theory, loop quantum gravity, and various other research programs, each offering partial insights, but none yet providing a fully validated, experimentally confirmed description of how gravity and quantum mechanics unify at the most fundamental level. This gap in fundamental physics means that the ultimate fate of closed time-like curves, and by extension, the deepest and most rigorous resolution of whether faster-than-light travel and time travel paradoxes can ever be physically realized, remains genuinely open, dependent on theoretical developments that have not yet occurred. Some physicists working in string theory and related frameworks have examined specific, simplified scenarios involving closed time-like curves and found results broadly consistent with chronology protection, suggesting that stringy corrections to classical general relativity tend to eliminate or destabilize would-be closed time-like curve solutions. Other theoretical investigations have found more ambiguous results, with certain highly simplified or symmetric model universes appearing to permit stable closed time-like curves even when quantum corrections are carefully accounted for, suggesting that chronology protection, if it holds at all, might not hold universally across every conceivable space-time geometry, but might instead depend sensitively on the specific details of the configuration under consideration. This theoretical uncertainty has practical implications for how physicists currently regard the entire question of faster-than-light travel and its associated paradoxes. Rather than treating the matter as definitively closed, with faster-than-light travel and time machines placed alongside perpetual motion machines as ideas conclusively ruled out by established physics, most physicists working in relativity and quantum gravity regard the question as provisionally, though very strongly, disfavored, resting on a substantial body of theoretical reasoning and indirect evidence, while acknowledging that a fully rigorous first principles proof remains elusive, pending further progress in quantum gravity research. This is a meaningfully different epistemic position than outright impossibility, and it explains why serious theoretical physicists continue to publish research examining closed time-like curves, wormhole stability, and related topics, not because they expect these investigations to reveal a practical pathway toward faster-than-light travel or time machines, but because fully understanding why these configurations fail, if indeed they do fail, requires working through the mathematics in careful and rigorous detail, mathematics that continues to reveal subtle and unexpected features of how quantum mechanics and gravity interact in extreme regimes. Parallel to the chronology protection research program, other physicists have approached the causality problem from a different angle, examining what would happen to information and computation itself if closed time-like curves did exist, regardless of whether nature ultimately permits their formation. This line of inquiry, pursued particularly within the field of quantum information theory, has produced some genuinely surprising results, suggesting that if closed time-like curves could exist and could be combined with quantum mechanical systems, the resulting theoretical framework would possess computational capabilities dramatically exceeding those of ordinary quantum computers, potentially allowing certain extraordinarily difficult computational problems to be solved with remarkable efficiency. These results, while entirely theoretical and contingent on the physical existence of closed time-like curves that remains unconfirmed, illustrate how deeply and unexpectedly the question of faster-than-light travel and time paradoxes connects to seemingly unrelated areas of physics, from cosmology and gravitational theory all the way to the abstract mathematics of computation and information processing. The investigation into chronology protection also intersects with ongoing research into the stability of wormholes and other exotic spacetime geometries under quantum corrections, an area that has seen renewed interest in recent years through developments connecting wormhole physics to the study of quantum entanglement discussed earlier. Some theoretical physicists have proposed deep and unexpected mathematical connections between the geometry of wormholes and the entanglement structure of quantum systems, suggesting, in highly speculative and still developing research programs, that certain forms of quantum entanglement might correspond, in a precise mathematical sense, to wormhole-like connections between regions of spacetime. This line of research remains firmly within the realm of theoretical exploration rather than established physics, and it does not suggest that ordinary entangled particles produced in laboratories are secretly connected by traversable wormholes capable of transmitting matter or usable information. But it illustrates the extent to which the deepest and most abstract questions about the nature of spacetime, causality, and quantum mechanics remain genuinely unresolved, connected through mathematical threads that physicists are still working to fully understand. Taken together, the chronology protection conjecture and its surrounding research program represent the current frontier of serious scientific investigation into whether the paradox-generating scenarios explored throughout this analysis, the tachyonic anti-telephone, the rotating universe's closed time-like curves, and the wormhole time machine, could ever actually be physically realized, or whether some deeper principle rooted in the yet incomplete marriage of quantum mechanics and gravity forbids them categorically. The honest and scientifically accurate answer, based on the current state of theoretical physics, is that the case remains open, constrained severely by established physics, but not yet closed with absolute mathematical certainty, a state of affairs that reflects both how much has been learned since Einstein first recognized the strange relationship between space, time, and the speed of light, and how much about the deepest structure of the universe remains to be understood. Standing back from the accumulated evidence assembled across this investigation, it becomes possible to see the full shape of the problem in a way that no single section could reveal on its own. The prohibition against faster-than-light travel was never a simple statement about velocity, the way a highway sign posts a numerical limit that engineers might someday find a clever way to exceed. It is a statement about the internal consistency of cause and effect, woven so deeply into the mathematics of relativity that every attempt to circumvent it, whether through hypothetical particles, exotic geometries, or quantum mechanical loopholes, runs directly into the same underlying obstacle. Energy requirements provide the first and most immediate barrier, rising without bound as any massive object approaches the light speed threshold. But behind that barrier lies a second, more fundamental one, rooted in the relativity of simultaneity and the structure of light cones, a barrier that would remain in force even if some future technology somehow discovered a way to supply unlimited energy. The tachyon hypothesis demonstrated this most directly, showing that even a hypothetical particle designed specifically to avoid the energy problem by existing permanently on the far side of the light barrier rather than crossing it, would still produce signals capable of arriving before they were sent, once the relativity of simultaneity was properly accounted for. The absence of any experimental confirmation for tachyons, despite decades of dedicated searching, aligns closely with the theoretical expectation that causality violation represents a genuine physical constraint rather than a limitation awaiting a clever technological workaround. The examination of closed time-like curves, first through the mathematics of a rotating universe, and later through the more physically suggestive mechanism of a wormhole with mouths separated by relative motion, revealed that general relativity's flexible treatment of space-time geometry does not automatically forbid these paradox-generating structures at the classical level. This finding forced physicists to look beyond classical general relativity entirely toward the developing intersection of quantum mechanics and gravity, where Hawking's chronology protection conjecture suggested that quantum field effects might act as an automatic safeguard, destabilizing any geometry that approaches the threshold of closed time-like curve formation before that threshold can actually be crossed. Yet, this conjecture remains unproven in full rigor, awaiting a complete theory of quantum gravity that continues to elude physicists despite decades of sustained effort across multiple competing theoretical frameworks. Alongside these genuinely troubling cases, the investigation also examined several categories of apparent faster-than-light phenomena that dissolve upon careful analysis into mundane and well-understood physics. Superluminal jets streaming from distant galactic nuclei reveal themselves as a geometric projection effect, arising from the alignment between a jet's direction of travel and an observer's line of sight, rather than any actual violation of the light speed limit. Cherenkov radiation demonstrates that particles can indeed exceed the speed of light within a material medium without ever approaching the more fundamental vacuum speed of light that relativity actually protects. The Opera neutrino anomaly illustrated how even a large, well-resourced scientific collaboration can encounter measurement artifacts capable of mimicking a genuine violation, and how the broader scientific community responds to such claims with exactly the intensity of scrutiny that an extraordinary result demands, ultimately tracing the anomaly to a loose fiber optic connector and a miscalibrated oscillator rather than any new physics. Quantum entanglement occupies a category of its own, producing correlations between distant particles that no theory involving local hidden variables could explain, as rigorously confirmed through Bell test experiments conducted with increasing precision over several decades. Yet the randomness inherent in individual quantum measurements ensures that these correlations can never be harnessed to transmit controllable information faster than light, a result formalized through the no-signaling theorems that follow directly from quantum mechanics' own mathematical structure. And the expansion of the universe itself demonstrates that recession velocities exceeding the speed of light are not only permitted, but currently occurring, for galaxies lying beyond the cosmic event horizon without producing any causality violation whatsoever, because this expansion involves the changing geometry of space-time itself rather than any object moving through its own local region of space faster than light. What emerges from placing all of these findings side by side is a picture considerably more nuanced than a simple prohibition. The universe appears to permit faster-than-light phenomena freely, whenever those phenomena cannot be used to transmit causally significant information backward through an observer's own light cone. Geometric illusions, medium-dependent effects, cosmic expansion, and the correlations of quantum entanglement all fall safely on the permitted side of this distinction. Tachyonic signaling, engineered closed time-like curves, and wormhole time machines fall on the forbidden side, not because they involve some different, more severe category of speed, but because they specifically threaten to carry information or influence into an observer's causal past, violating the strict ordering of cause and effect that every confirmed prediction of relativity depends upon. This distinction offers a way of understanding why the light-speed barrier has proven so remarkably durable across more than a century of increasingly precise experimental tests, from the null results of 19th-century ether detection experiments through the confirmed time dilation observed in particle accelerators and atomic clocks to the modern gravitational wave detections that continue to validate general relativity's predictions with extraordinary precision. Each new test has offered an opportunity for some deviation to appear, some hint that the light speed limit might be approximate rather than absolute, and none has ever found one. This consistency does not prove, in the strict logical sense, that faster-than-light travel is absolutely and eternally impossible under every conceivable future refinement of physical theory. Science generally avoids claims of that particular kind of certainty, preferring instead to describe theories as extraordinarily well confirmed within their tested domain, while remaining open to revision should new evidence eventually demand it. But the specific character of the evidence assembled here suggests something stronger than ordinary scientific caution alone would require. The obstacles to faster-than-light travel are not merely empirical, in the sense of simply never having been observed despite reasonable efforts to look for them. They are structural, emerging directly from the mathematical relationship between space, time, energy, and causality that underlies the entire framework of relativity. A framework confirmed not through a single decisive experiment, but through an enormous and interlocking body of evidence spanning particle physics, astrophysics, cosmology, and precision timekeeping technology used every day in global positioning systems. When a prohibition emerges this deeply and this consistently from a theoretical structure, this thoroughly tested, it carries a different kind of weight than a simple observational gap awaiting future discovery. And yet the story told throughout this investigation resists a simple, closed ending, precisely because the deepest and most rigorous resolution of these questions depends on a theory of quantum gravity that does not yet exist. Chronology protection remains a conjecture supported by suggestive semi-classical calculations, but not yet elevated to the status of a proven theorem. The stability of hypothetical wormholes under quantum corrections remains an active subject of theoretical research, connected in unexpected ways to the study of quantum entanglement and the emerging field of quantum information theory. String theory and other candidate frameworks for quantum gravity continue to explore how closed time-like curves behave once quantum corrections to space-time geometry itself are properly accounted for, producing results that vary depending on the specific model under consideration rather than converging on a single, universal answer. This unresolved territory is not a weakness in the scientific understanding assembled here. It is an accurate reflection of where the genuine frontier of physics currently lies, A frontier where the well-established, thoroughly tested framework of relativity and quantum mechanics is currently understood meets the unknown territory of how these two frameworks ultimately unify at the most fundamental level. Physicists studying this frontier are not searching for a way to build a faster-than-light spacecraft or a functioning time machine, goals that the overwhelming weight of current evidence suggests will remain permanently out of reach. They are searching for a deeper and more complete understanding of why the universe is structured the way it is, why causality holds together as rigidly as it does across every test conducted so far, and whether that rigidity reflects an absolute, inviolable feature of reality or a constraint that emerges from the specific physical conditions of the universe humans happen to inhabit, potentially subject to exceptions in circumstances not yet encountered or fully understood. The light speed barrier, examined from every angle available to modern physics, from the energy requirements of acceleration through the geometry of light cones and the mathematics of tachyons, through the exotic possibilities of rotating universes and wormhole time machines, through the careful resolution of superluminal jets and Cherenkov radiation and the Opera anomaly, through the subtle distinction between quantum correlation and genuine communication, and finally, through the expanding geometry of the cosmos itself, reveals itself not as an arbitrary rule imposed upon an otherwise unconstrained universe, but as a reflection of something more fundamental about how cause and effect are permitted to unfold across space and time. Whether that reflection will someday be shown to admit rare, carefully constrained exceptions, uncovered through a future theory of quantum gravity not yet written, or whether it will instead be confirmed as an absolute and permanent feature of physical law, remains one of the open questions at the heart of theoretical physics, a question that continues to draw serious scientific attention precisely because so much has already been learned, and because what remains unknown sits at the very foundation of how the universe holds itself together, one carefully ordered moment after another.